This is a flashback to Chemistry 221, right around the time we did the net ionics lab, and we use this as a kind of a general rule to tell if something was aqueous, i.e. if it dissolved, or if it was insoluble, i.e. if there was a solid. We use this to figure out when compounds were solids and not. We talked about how nitrate, ammonium, sodium, potassium, these kind of things, almost always AQ. I highlighted at the time how chloride, bromide, and iodide are AQ except with silver plus, mercury 2,2 plus, and lead 2 plus. And most of the negative anions, especially the polyatomic ions, are insoluble unless they're with sodium, potassium, ammonium, stuff like that. So on the right-hand side, here's like an overview and a reminder how to use this guide. Barium nitrate, if I asked if it was soluble in water, you would say soluble, because nitrate, if you look there in the upper left-hand corner, nitrate is one of the ones always AQ. There's no exceptions to the right. So we would say AQ. It dissolves really well in water. Now, barium chloride has a chloride, and most chlorides are soluble, i.e. you'd write AQ, unless the chloride, bromide, or iodide are with silver, mercury, and lead. And barium is certainly not one of those, so we would say it's AQ, it's soluble in water, and it is. On the other hand, if I asked you about barium sulfate, if it was water soluble, well, sulfates there are usually aqueous, usually soluble, but there are some exceptions, and a very notable exception is the barium. So because barium's an exception, that means BaSO4 is quite insoluble, and you wouldn't want to write BaSO4 AQ because it doesn't dissolve really well. You'd want to write BaSO4 solid to show that it's insoluble. So these are the rules we used in Chem 221. We're now going to look at a whole new series of rules, which will still use this particular guide. However, we're going to look at much better rules here coming up. So when a chemist uses insoluble, that means that the compound does not dissolve well in water. On the other hand, soluble compounds dissolve very well in water. But you can write equilibria for all of these, even for things like sodium chloride, which is very, very water soluble. So NaCl solid can be written in an equilibrium as dissolving into Na plus aqueous plus Cl minus aqueous. Remember, the ionic compounds don't just dissolve, they dissociate into their ions. So you have two ions coming for every NaCl that dissolves. The solubility of sodium chloride is exceeded when the solid precipitate doesn't dissolve anymore. Remember, solubility is like a threshold, and once you go past that threshold, maybe it's like 0.1 grams, maybe it's 200 grams, who knows? But whatever that number, when you go past it, that's when you begin to form a solid. The precipitate doesn't dissolve anymore. And so even the most insoluble compounds do dissolve to a small extent. As long as you know the details of the reaction, you can make predictions.
When a small amount of sodium chloride is added to 100 grams of water, it dissolves. If we add more and more salt, eventually no more can dissolve in this amount of water. The quantity of salt dissolved in this solution, about 35 grams at room temperature, is a measure of sodium chloride's solubility in water.
So in that video, for that amount of water, which is roughly 100 milliliters or so, it took 35 grams of sodium chloride until you begin to see a solid. So under 35 grams, you didn't see a solid, but 35 grams or more you did. So we would say that the solubility of sodium chloride in that case is about 35 grams. But notice that we could change the volume of the solvent, water. You could add more, and that would make it dissolve. You could probably change the temperature, which you definitely could, and that would make it probably dissolve more if you increased the temperature and decrease if you decreased it, stuff like that. So all of these are factors that chemists think about when they're talking about the solubility, like what's the threshold to make a solid appear, or what's the threshold we have to go under to make the solid disappear. The silver group is three ions, the silver plus, the lead 2 plus, and the mercury 2,2 plus ions, and they all react very similar to each other. And so in this example, when you add chloride to any one of those, they all form insoluble compounds, all right? You see a precipitate. Now, They do dissolve a little bit, all right, even in the most concentrated forms, but it's pretty small. So even these insoluble compounds will have some ions over them, all right, and that's an important consideration. So these all have a threshold, a solubility, and once you go over it, that's when you see a solid. And for all three of these with chloride, as well as bromide and iodide, they're pretty small numbers.
When moderately concentrated solutions containing silver ions and chloride ions are mixed, the resulting solution is supersaturated with silver chloride. A precipitation reaction occurs until the system reaches equilibrium. In this model, the red and white molecules are water. Chloride and silver ions, gray and green respectively, are in solution. When they encounter each other, they bond and bind with other silver chloride molecules that have precipitated from solution to form the solid.
Solvent molecules, i.e. water, usually outnumber the solutes like silver and chloride ions by quite a bit. However, somehow the attraction of these two is so strong that they will find themselves, and to a pretty small extent, until they start to form the ionic solids, and that's the silver chloride that you see. So again, it's amazing that any of these compounds form, and especially when they form in such low concentrations, and that shows there's really an attraction between the cation and the anion. So once an equilibrium has been established, and it usually doesn't take too long, you can't have any more silver chloride dissolved in the solution. And this is called the saturation point, and the solution is said to be saturated. So in the little graphic down there, on the left-hand side, you don't have a lot of purple AgCl. It's unsaturated. You can add more AgCl. But you get to a point where nucleation, i.e. forming a solid, begins to occur. That points out that you are then past the point of saturation, and you're beginning to see a solid. A saturated solution is just a solution that cannot dissolve any additional solid, all right? Now, if you increase the volume, you can probably put some more in. And again, you can change the temperature even, but for that temperature and for that amount of volume, you can't dissolve any more solute. So the solubility is just literally the maximum amount of solute that can be dissolved for that volume of solvent. And solubility is usually in moles per liter, but sometimes you'll see it in grams per liter, grams per milliliter, stuff like that. Silver chloride has been studied extensively, and at 25 degrees Celsius, the solubility is 1.67 times 10 to the minus 5 moles per liter. So what that's saying is that at room temperature, you can, in 1 liter of water, you can dissolve 1.67 times 10 to the minus 5 moles of silver chloride. And that's not a lot. We could figure out the moles and grams and all that kind of stuff. It's not a lot, though, however, and that's why it's easy to see the AgCl precipitate. The solubility equals the dissolved ion concentrations, because at that 1.67 times 10 to the minus 5 molar number, that's when you have silver plus and chloride ions equal to the same concentration. So when you get to that point, the silver plus and the chloride concentrations are also equal to solubility. Notice that 1 silver plus and 1 chloride came from AgCl. So if you have the solubility, the amount of moles of AgCl that dissolve per liter, that's going to equal the dissolved silver plus and the dissolved chloride concentrations at the same time. If a saturated silver chloride solution has a solubility of 1.6 times 10 to the minus 5 moles per liter, and that equals the concentration of the silver plus and the chloride, there's some kind of cool stuff we can do here. You can calculate an equilibrium constant K based on this reaction. Now, notice the form of this equilibrium constant. The solid is the reactant, for example, AgCl, and the ions that go into it are the products, i.e. silver plus and chloride. So remembering that solids and liquids never go on the equilibrium expressions, the K value would be the silver plus concentration times the chloride concentration divided by 1. Don't include the solids and liquids. And each silver plus and chloride are both equal to 1.6 times 10 to the minus 5. So it's like solubility squared, 1.67 times 10 to the minus 5 times 1.67 times 10 to the minus 5, which comes out to be 2.79 times 10 to the minus 10th. And this type of equilibrium constant gets a fancy name. It's called Ksp. It's the solubility product constant. This equilibrium constant arose because it was the product, i.e. we multiplied the solubilities by each other. So Ksp is the product of solubility, the solubility product constant. And that's what we're going to talk about a lot this quarter. So if you're talking about Ksp, the solid precipitate will always be your reactant, and then the ions that go into it will be your products. And that's how all of these Ksp systems are set up. Notice that the Ksp value is less than 1. Less than 1 for an equilibrium constant means you have more reactant than product. That means we're going to have more solid, undissolved solid, than we will have the ions. This is definitely a reactant-favored K. That's why the solid is preferred over these ions in general.
When solid lead chloride is added to water, a small number of ions are released into solution. Those ions can reattach to the solid, while other ions can dissolve. A state of dynamic equilibrium is reached, in which the concentrations of ions are constant and can be described by an equilibrium constant expression.
This is the equilibrium constant expression for lead 2 chloride. So PbCl2 solid is the reactant, and lead 2 plus and 2 chloride ions would be the products. The Ksp for this reaction is quite well known. It's 1.9 times 10 to the minus 5. And how they got that, Ksp here would equal the lead 2 plus concentration times the chloride ion concentration squared, since there's 2 of them, and you would divide by 1 because there's nothing in the reactant side. Don't include solids and liquids. Here's some representative Ksps of different values, and none of these are the numbers you have to use. We're going to do a lab in Chem 223 where we're going to use that calcium hydroxide Ksp. So keep that in the back of your mind. That might come in handy. But all of these Ksps are less than 1. That shows that they're all very insoluble in water. This question asks, which of the following correctly displays the equation used to describe the Ksp for barium fluoride? Barium fluoride dissolved in water, which is basically what all of these are going to be, by the way. But anyway, in a Ksp expression, the solid is the reactant, and the ions that go into it are the products. So the first one has barium fluoride solid. Barium is positive 2, fluoride's negative 1, so you need 2 of them to balance the barium. It would be insoluble, so you'd write an S next to it. So I like the reactant part of A, but the product is incorrect. That just shows dissolved barium fluoride, and honestly, that's not what we're after. We want the dissolved ions. So if you look at B, that's getting warmer. You've got a barium 2 plus ion, but fluoride ions are F minus, and they don't like to be next to each other. So I don't know what that F2 minus thing is, and that's kind of weird. However, answer C has the solid barium fluoride, digging it, and the ions that go into it would be barium 2 plus ions, AQ, plus 2 fluorides, AQ. I'm liking that. So answer C looks like a really good answer. D doesn't have the right stoichiometry, or the right formula for that matter. Barium is positive 2, fluorides minus 1. That wouldn't be a correct formula. And the last one is basically the opposite of a Ksp. Everything's flipped. The solid is the product, the ions are the reactants. Don't use that. So again, Ksps, the solids will be the reactant, and the ions that go into it will be the products. Now, solubility and Ksp are different numbers, and that's really important to point out here. Solubility is usually expressed as the mass or moles of solute dissolved in a liter or 100 milliliters or something like that, all right? It's usually, for us, it'll be moles per liter, but it can be expressed different ways. So solubility is a molarity, and Ksp is the product of solubilities. So, for example, in that one problem, we took the solubility and multiplied it by itself, the silver plus times the, I think it was chloride, to get the Ksp value. So Ksp and soluble are different. So on the right-hand side there, we've got lead 2 iodide dissolving in water. So the Ksp expression would have the solid as the reactant. The ions that go into it are products. And we can use the solubility to calculate Ksp. The solubility here, 1.30 times 10 to the minus 3 moles per liter. And again, what that's saying is that for every liter of water, you should be able to dissolve 1.30 times 10 to the minus 3 moles lead 2 iodide. But you go over that, you'll see a solid, stay under it, and you should see everything dissolve. Solubility, X, is how much PbI2 breaks down. And for every soluble X that breaks down, you're going to have another X of lead 2 plus, like it's a 1-to-1 ratio, and you'll have 2X, or twice that amount, for the iodide. So the solubility is the moles per liter of lead 2 iodide that break up. And for every PbI2, you're going to have 1 mole of lead, so the same number can be used for the lead 2 plus concentration. However, the iodide will be twice that number. There are 2 iodides for every lead, 2 iodides for every PbI2. So we'll multiply that number by 2 in order to find the concentration of the iodide. So iodide would be 2.60 times 10 to the minus 3. Anyway, you put those two numbers together. We want to calculate Ksp. So you've got the lead is 1.30 times 10 to the minus 3. The iodide is twice that number, 2.60 times 10 to the minus 3. You can throw this all together. You want to square the iodide because it's iodide squared. Ksp 8.79 times 10 to the minus 9. So the solubility here was 1.30 times 10 to the minus 3, and the Ksp 8.79 times 10 to the minus 9. Quite different numbers. Ksp and solubility are different. So in this question, the solubility of barium sulfate is found to be 1.05 times 10 to the minus 5. What's the Ksp value? Okay, so first we need to figure out what the Ksp expression is going to look like. Now, barium sulfate is BaSO4, and it is quite insoluble. However, like all insoluble things, it is soluble to a certain extent. So the equilibrium would have BaSO4 on the reactant side, and on the product side, you'd have barium 2 plus ions, and you'd have sulfate ions, SO4 2 minus. Now, for every barium sulfate that breaks down, you're going to have 1 barium ion and 1 sulfate ion. And why that's important then is that the concentration of the barium 2 plus ion, as well as the concentration of the sulfate ion, will be equal to the solubility. So since Ksp is the product of solubility, you'll take the barium times the sulfate. We'll take the 1.05 times 10 to the minus 5 number and use it for barium, and then multiply it by the same number for sulfate because it's the same compound. 1.10 times 10 to the minus 10. So again, Ksp equals barium times sulfate equals X times X. If you use solubility, that sometimes is seen as X. So if you square X, you are good to go.